Alright, today we're going to do the coupled harmonic oscillator. So let's say we have a system of two masses with the same mass, M. You have springs between them, all with the spring constant K. Let's call this spring A, B, and then C. Mass 1 oscillates with displacement x1, mass 2 with x2. Let's try build a general case for the motion of these masses. So let's start by calculating the force on mass 1. So F1 on the spring A is just minus K x1. And F1 B is just, it's going to depend because when this is stretched, this is compressed. So it's going to relate to the displacement of x2 as well. It's going to be minus x1 minus x2. Then the total force is just going to be these two added up. So F1 total is going to be minus K 2x1 minus x2. You can do the same for the second mass, which would literally just be this flip. Then do that. F2 total minus K x2 minus x1. These all have the same spring constants. Alright, so what we learned from the last video, Newton's second law, F equals ma. If we rewrite this, we can get x over 1, let's do the first one, which is acceleration equals minus k over m 2x1 minus x2 for x2 double dot minus k over m 2x1 minus x2. Cool. I'm going to rewrite this k over m actually. The call from last video, omega naught is equal to, defined as k over m. So let's do that. Minus omega squared, omega naught squared. Minus omega naught squared. Alright. Can you see that? Yeah. So you have two differential equations. But we can't solve these ordinarily. Because x1 relies on x1 and x2. And x2 relies on x1 and x2, so we can't do the normally. So what we can do is think about how this moves. And the only way we can relate these two is think about it if they're moving with the same frequency. So when they're in phase, they're going to move like this, like a unit. The center spring B is not going to stretch or compress, it's just going to be moving with them. But when it's out of phase, the mass is going to be moving like this. And we can just think of B as like a solid wall. So let's do that. So when they're in phase, at the same frequency, the omega 1, omega 2 is equal to omega. And don't get confused, omega naught is not the same as omega 1. Alright. Let's write this clearer. So equals Alright, so now we can solve them using ansatz. So x1 equals e I omega t, and x2 equals e I omega t. So then if we differentiate with respect to t twice, we're gonna get C1, C2. We're gonna C plus C1 over C2 minus omega squared EI omega T. Now we can sub this in for 1 and 2 into this equation. So we're gonna get minus C1 omega squared EI omega T equals minus omega naught squared 2C1 minus C2 EI omega T. I've just factored out the, so we can cancel a lot. We cancel down, cancel the minus signs, cancel out the e's. And we're gonna get nice equations. We're gonna get C1 omega squared equals 2C1 minus C2. Same for C2, we're gonna get, forgot that, equal 2C2 that's what we're left with right now. So actually I'm gonna rewrite this to minus C1 plus 2C2. I'll just change the order. So let's put this into vector form. We're gonna get omega squared C1 C2 equal to omega naught squared 2 minus 1 2 C1 C2. Cool. So if you done maths, matrices, you know that what's it called? A scalar times a vector, that gives you a matrix and a vector. Then this is an eigenvalue. We can work that out with the formula. That let's call this matrix A. So we're gonna know that the determinant of A minus the eigenvalue omega squared times by the identity matrix is equal to 0. So then we can work out what omega is. So let's do that. Yep. Okay. So A minus omega squared I. So it's gonna be 2 omega naught squared minus omega squared. And this is gonna be minus omega naught squared minus omega naught squared 2 omega naught squared minus. That equals 0. No? Doesn't equal, the determinant of this equals 0. So 2 omega, recall determinant AD minus BC for a 2 by 2 matrix. Squared minus omega squared equals 0. So if we just solve this, simple. We're just gonna get omega squared equals 2k over m. I'm just putting this back in. Plus or minus, because it's square here. K over m. So we get two solutions because it's either in phase or out of phase when you're moving with the same frequency. So let's say omega squared plus, let's just rename them. It's going to equal 3k over m. And omega squared minus is equal to k over m. See that? Now we can start to build our general solution. So a second order differential equation, we usually want it in the form of A E omega t plus B I omega t. Okay, So let's get the C's, the constants in terms of each other by subbing it in. So when you sub in for omega minus, we're gonna get a C1 minus is equal to C2 minus. Oh yeah, let me put that back in. This omega plus and this omega minus. When we sub in for 3k over m, which is omega plus, we're gonna get C1 plus equals minus C2 plus. I'm skipping a lot of steps, but it's easier to see. So now we can build the final general solution that describes the motion of a coupled harmonic oscillator. So x1 equals C1 E I omega plus T plus C1 minus E I omega minus T. And then for x2, C2 plus E I omega minus T plus C2 minus E I omega minus T. Now, we did these corrections to make it easier. So now we can just rewrite x1 and x2 as a whole. So we can just get forget C1 and C2s, we can just write it as a constant A. So x1 equals A E I omega plus T plus B E I omega minus T. A, which is C1 plus. C1 plus equals minus C2 plus, so you can just write minus A E plus, which is B, which is C1 minus equals C, so you can just write B. And those are the two equations that describe the motion of a coupled harmonic oscillator.